We're looking to prove, it says prove the polynomial identity for the square of a binomial representing a difference. We're trying to show that a minus b all to what power, kids? Equals what? Plus what? Okay, so what this is really saying is show that this is equal to this. Well guys, when you say a minus b squared, that means take a minus b times what? Okay, so we're going to show that this is equal, all right? So we would go ahead and FOIL this out. So the first thing we're going to have is a times a, which would be what, kids? Careful.
A squared.
All right. And then a times negative b minus ab. Now kids, when you start putting multiple letters together like ab, I would start putting letters together in alphabetical order. And the reason I tell you to put them together in alphabetical order is because it's easier to combine like terms when you have to simplify stuff in the end. So right here, when we start multiplying negative b times a, how should I express that if I want to go alphabetically? Negative ab again, right? And then how about your negative b times negative b, kids?
Positive b squared.
Okay, now as I look at this right here, after I've gotten rid of the parentheses, after I've expanded this, anything going to combine? How many minus ab's do we have? So it's a squared minus 2ab plus b squared. Kids, have we shown right here that have I shown that these two expressions are equal? Have I shown that they're equal? So an identity for a minus b squared is a squared minus what? 2ab plus b squared. Now, I'm not going to get too technical with this next part right here because they're going to say use the square of the binomial in part A to calculate 24 squared. Now guys, if I wanted you to calculate 24 squared, what would I tell you to do? Just punch it in your calculator. Okay? What is 24 squared? Somebody check that for me. 576, you say? Is that what I heard?
Yeah.
Okay. So what they're saying right here is, hey, could you show that 24 squared is 576 by using this binomial theorem? Well, what they're asking you to do is this. Guys, what number really close to 24 is pretty easy to work with? 25. What would you do to the 25 to turn that into a 24? What they want you to do here is say, ooh, let's just see if this works to show that 24 squared is 576. What they want you to do is to do 25 minus 1 all to the second power, and they want you to plug values in for a and b up here to see if that equals 576. So in this situation, what's your a value kind of like? $25. What's your b value kind of like? 1, right? Okay, let's plug it in. A squared would be what squared if we want to check this? See if this formula worked for getting this. A squared would be 25 squared, wouldn't it? Minus 2 times, what would you throw in for A?
25.
Ah, I'm sorry.
24.
25, I had 1 in there. Okay, what would go in for B then? 1. The only time I've ever felt like a volleyball player. Okay. Don't you guys still do stuff like that?
Yeah, we do.
Good. All right, and then plus b squared would be plus what, kids? Okay, help me out. What is 25 squared, somebody? 625, good. Okay, and then 2 times 25 times 1, we should be able to do that mentally. 50, and then plus what?
1 squared.
Okay, so this would really be 625 minus 50 plus 1. Again, guys, we know 24 squared is already going to be what? 576, okay? So,
They are the same.
what's 625 minus 50 plus 1?
575. Plus 1 is 575.
Yep, that equals 576, doesn't it? So my question, kids, is this. When I expand a minus b and square that out and call it a squared minus 2ab plus b squared, does it work numerically for us as well? Show that 24 squared is indeed 576. So do you understand why the two parts I have highlighted up here are equivalent to each other? Okay, and we say since these are equal expressions, these two expressions are an identity for each other. They mean exactly the same thing. Okay. Now down below here, I've got a kind of a cheater chart here for you. I screwed one of these up. I really messed this second one up. I want you to change this right here. Okay. I messed this up big time. This here should be just like we just did. In the square binomial, there should be two parts to this. And what it should have said was a minus b all to the second power. I'll pull this up here quickly. Should have been a minus, that's a minus b to the second power equals a squared minus 2ab plus b squared. Okay, and I'm going to provide you some examples here, okay, here in a second, in terms of what they equal. Guys, in a binomial, how many parts to a binomial? What's the prefix bi mean? What value? 2. Okay, there's two parts, a first part and a second part. So that means there's one sign in between the two parts. All right, let's talk about the first one right here. Guys, there's a rule up here. These are product of binomial rules right here. Product of binomials. And the first one's called a sum and a difference rule. Okay? If you notice over here, you have a and b in here, but what sign is in between this first one? And what's here? A subtraction sign. Okay, if that ever happens, I'm going to give you an example right here. If that ever happens, I'm going to show you why this is a squared minus b squared here quickly. What would the a times the a get you? What would the a times the minus b get you? Negative ab. Again, keep in mind when you're putting multiple letters together, you probably want to group them how? Alphabetically. So I've taken a times everything. Now let's take this positive b times everything over here. What's b times a? It's pretty BA, but we're going to call it AB. All right. And then positive B times negative B would be minus B squared. Well, guys, if you notice right here in the middle, a negative AB and a positive AB, what are they going to do to each other? So the only thing you're left with is what? A squared minus. Okay. So let me give you an example. This is called sum and difference. And what they're saying is the terms in here are the same, but one is a sum with the addition sign, and one's going to be a difference right here with the negative sign or a subtraction sign. So let me give you an example right here. Suppose we had, I don't know, should I make this easy or difficult for you?
Easy.
Okay, suppose I had 2x plus 4, that's my first binomial, times 2x minus 4. First of all, aren't the 2x and the 4 kind of alike right here? Well, inside of one of the binomials there's addition, and inside the other binomial there is subtraction. Well, this is called the sum and difference rule. And so by rule, this is just going to become the first term squared minus the second term squared. So really 2x times 2x will be the first part, which is what? 4x to the? And then how about the plus 4 and minus 4? Times. Okay, so 4 and 4, or the b squared, right? Minus b squared, or 4 squared, which would be minus 16, right? There it is. Okay. That only works when you have the same terms inside, but there's a plus sign in one of them and a minus sign in the other. And here's why. Think about this. What would this positive 4 times 2x make? Wouldn't that make 8x? What's the minus 4 and 2x make? What's a positive 8x and negative 8x going to do to each other in the middle? They just drop out. Okay, quickly, here's an example. You guys tell me. We used 2 already. Let's go. Real quickly, what's that going to expand to be?
9x squared. Plus minus 14.
9x squared minus 49. Square them. What?
Are you hot?
Am I pitting?
Look
Woo!
at your other one. It's like a little circle.
Oh, you guys use bears.
Remember?
I'm sorry, I can't.
You know, it's hard work being a math teacher.
It's also hot.
It's hot.
Is it hot in here?
Yes.
I'm sorry. I hope I didn't gross anybody out. I hope I didn't gross you out to the point that there were fingernails in a water bottle.
Yeah. Freaking weirdos.
Yeah. Okay. Okay, so let's take a look at, whoops, I didn't want to do that. Boy, you guys know how to throw a curveball by me easily, don't you? Okay, what's the next type of square of a binomial? Okay, the only difference here is this, kids. There's just one difference, okay? Square of a binomial means you're taking a plus b times itself. And here's what you end up with, kids. You end up with a squared plus what? 2ab plus what? Okay? And we've kind of talked about this one. What if you have a minus b squared? Well, it turns out to be a to the second minus 2 times a times b plus what? And didn't we just show this one up here in that identity up here? We did, didn't we? Okay, so take my word for this first. These are going to work. Square of a binomial. So what this is saying right here, kids, is this. What if I had, say, I don't know, let's go 2x, let's go 2x plus 3 here, all to the second power. Now, I could write this out, kids. Watch what I do here. I'm going to write this out. You don't need to write this out on the board. Just watch what I do here. Do you guys agree that 2x plus 3 squared is still 2x plus 3 times 2x plus 3? Okay, so what's 2x times 2x going to get you?
4x squared.
Okay, what's the 2x times the 3 going to get you? And what's 3 times 2x?
6.
And then 3 times 3 would be? And I'm not going to tell you, if you want to go through and do stuff like that, I'm okay with that, okay? I'm totally okay with that, because right here you can combine the 6x and 6x to be what? Okay? If you're comfortable doing that, by all means do that. But this rule is saying up here, you know what? We could let the a value be like the what here, kids? And we could let the b value be like 3. So according to this right here, we have a mess like this. We want to make it look like this and see what it would expand out to be. So the a part squared would be 2x times 2x, wouldn't it? Wouldn't that be 4x squared, kids? Okay, now think about this one. Plus 2 times a. So what's 2 times a, kids? Careful. What would 2 times the 2x be? 4x, then times b of 3 would be what? Careful. 4 times 3?
12.
Wouldn't that be 12x? See what I did here? 2 times 2x is 4x, times the 3 is 12x, and then b squared would be 3 times 3, wouldn't it, kids? Does that match what we had over there by expanding longhand? Okay. Basically, did something instead of doing it in 2 steps, we did it in 1 step. Okay? Okay. All right, so then the last one here, kids, we'll do a difference here. Make sure you're okay with this, but cube of a binomial. Here's your rules. If it's a plus b to the third, use this. If it's a minus b to the third, use what? Okay, let's do one that's to the third power. But we'll do one with a difference, okay? Give me something, kids. 5p minus 6, all to the third power. Okay, let's see what this equals. All right. Do you agree that this expression, this binomial to the third power, is kind of like this binomial to the third power? It's minus. In the parentheses, it's to the third power. So the first thing it says is take a to the third. What are you kind of using as your a value here, kids? 5 what? P. So you'd have to take 5p times 5p times 5p. 125p to the what? Okay. Now it says minus 3 times a squared. So I've got to do minus. Okay, so we need to know what a squared is first, don't we, kids? 25p squared times what here? So times 3, and then times the b value is really 6, isn't it, kids? Because it says. Okay, so do this for me. Go 25 times 3 times 6. What is that? How much?
450.
Yeah. So minus 450 p squared, right? Right? Because 5p times 5p was 25p squared. We times the 6. That's 150 times the 3 would be 450. I agree. Now we're at this part, the plus 3ab squared. So we've got 3 times what here, kids? So 3 times 5p, right? Which would be 15p times 6 squared, right? What is 6 squared? 36 times 15. Boy, I hope you get 480 out of that. No. 540. So you should get 540p, right? And then the last part is minus b to the third. So your b value is 6. So 6 to the third would be what? 216. So minus 216. Whoa. So there it is, minus 216. Now, guys, I really think that for purposes here, this chart's really important. Okay, and we're going to kind of refer back to things. Monday, when you have a work day on things, make sure you bring your notes. This is going to be pretty important to refer to. Okay, it talks about again sum and difference of a binomial product, square of a binomial, cube of a binomial. Okay. Now we're going to look at some different things here, and in fact, I'm going to have you try some examples on your own. On the next page here, everybody ready for next page? No? I'm wondering if everybody has everything down. Okay, what I would like you guys to do is to try those rules that we just did. So example 6, I want you guys on your own to try those 3 right there. Why be careful on that last one. That last one's going to be tricky. Okay? You guys take a couple minutes and try those, okay? See what kind of rule you're using and use your rules to figure it out.
I don't work that fast. Try. I'll try that.
Talk with your table partners, see what they say. First one should be really easy.
Well, good for you. Okay, I'll stop.
back of that. Ow. Oh, look back. Yeah, no, I have this one. I don't need this. Yeah, I'm good. Yes. Did I do something to upset you? Oh my God.
All right, I think the first two you might have down pretty well. Should we say that last one for together?
Yeah.
Yes.
Let's do that, okay? How about a volunteer for my first one? Is this a sum and difference? Is this a product of, or is this a square of binomials, or is this a cube of binomials? Sum and difference is nice. It's just a squared minus b squared. So what do you end up with here?
4x squared minus 4x.
All right, say again, I didn't catch all that.
4x squared minus 4x.
Yep, the 2x and 2x would be 4x squared. Whoops. Would be 4x squared. And then the 7 squared would be minus 49. How many had 4x squared minus 49 there for that one? Love it. Okay, that's the simple one. This one here, not too bad. It's a square of a binomial we're adding. So we would have used the identity a squared plus 2ab plus b squared. So help me out, kids. What would a squared become in this? 16y to the, right? And then 2ab plus 24y. Awesome. And then what? Very good. Very good. Love it. It's pretty easy, isn't it? Okay, and then the third one gets a little difficult because here's the deal. In that first term for cubing something, how many letters are really there? 2. This is going to get tricky. I'm going to make this a little bigger here. Write small, okay? All right. First of all, this is the cube of a binomial, right? And the cube of a binomial is going to have an identity of a cubed plus 3a squared b plus 3ab squared plus b to the third. Okay? All right. Everywhere where you see an a up there, what are you really plugging in, kids? And everywhere where you see a b up here, you're really plugging in what? That's why it gets kind of confusing, because they chose which variables to work with our identity. Okay, so everywhere there's an a, what's going in? Okay, this is going to become ab to the what first, kids? Plus 3 times what's going in for a to the times the b value, which is now 2. Boy, I don't know if I'm going to be able to fit this in here. I'm going to try. Plus 3 times what? Times b to the what? B to the, so 2 to the, okay, and then finally plus b to the third, so it'll be plus 2 to the third power. Okay. All right, kids, here's the situation when you're putting stuff in or solution-wise. What they're going to end up doing is they're going to say, I don't want to see all those parentheses up there. I want them to go away. All right, and here's how we make them go away. We can bring this 3 into every one right here. So AB times AB times AB would really be a to what power first? Third, and then times b to the what? So this part right here becomes a to the third, b to the third. Okay? Now, help me out, kids. What's 3 times 2 going to get you?
6.
For that term, it would be 6. And I don't want this like this, so it'll be 6a to the what? Second. And then b to the what?
Second.
Okay, so we've taken care of that part. Over here, I'm right in this area here. What's 2 squared? 4 times 3? 12 times, so plus 12ab. Finally, plus 2 cubed, which is what? There she is. There it be. That's not so bad, is it? Okay. Now, guys, we've used these rules for products of binomials, and they're special rules. They're great rules. Okay? But, do you guys remember that sheet I gave you that had Pascal's triangle on it? This triangle makes life so much easier for you. Okay? Can I show you how to use that triangle to make life a lot easier for you?
This looks like an eye test.
Looks like an eye test? Okay, Grace, go. 7th row. No, you failed. Glasses, now. Okay.
That's literally how it's
All right. Let's talk about this triangle real quickly. This triangle real quickly. I'm going to draw a part of it. Do you guys have your triangle handy?
Yeah, it looks like a bunch of bowling.
Here it is.
Nope. I'll go this far. Okay. Guys, what do you know about anything to the 0 power? What's it equal? 1. Why does anything to the 0 power equal 1? Because it just does, right?
Yeah.
Listen carefully, quick. Please hear this out. I want you to understand why something to the 0 power equals 1. This drives me nuts that we don't know this. We should know this. All right. What's 5 divided by 5? 1. Okay, now here's the situation. Think about this as like 5 to the 6th power over 5 to the 6th power. Right? That would still equal what value? 1. But when you have like bases like this and you're dividing, what do you do with exponents? How many 5s are really up here?
6.
How many 5s are really up here? How many 5s are going to be left up top? If there's 6 5s up top and 6 5s on the bottom, aren't they all going to cancel?
Yes.
That's like having how many 5s left both up at the top and the bottom? None. Or I could say this is the same as 5 to the 6 minus 6 power, isn't it? Which is equal to 5 to the 0. That is why anything to the 0 power will equal 1, because these exponents right here, 5 to the 6th over 5 to the 6th is one number or the same exact number, which would divide out to be 1, but 6 minus 6 exponent-wise is what value? 0. Now, do you understand why stuff to the 0 power is 1?
Yes.
Okay, understand that. So here's the deal. If anything... Break my chair again? Break my chair again? I'm not going to be very nice today.
What's the enemy?
My chair, that was the last time somebody broke my chair. I'm not going to stand for it anymore. Okay? Why understand up here? You need to do this on your triangle. This is what I want. Okay, I've been called for pitting out. I've been called for yelling about broken chairs. Kind of break your triangle up. Kind of lock that up.
All of them?
Yes, we're going to have some. Not all of them. Just maybe the first 4 or 5. Okay. You have to make sure you understand how we're going to identify these or name these in order to be able to kind of use this triangle to make life a lot easier for you, okay? We just got done saying anything to the 0 power is simply what value? 1. So Pascal's triangle is based on that idea that anything to the 0 power is 1. We're going to call these up here rows. And it turns out that this first row is going to be row 0. Okay? Because anything to the 0 power is going to be what? 1. Okay? So if this is row 0, what do you think we're going to call this? I want you to notice something. Next one's going to be row 2. Hey, the first number listed here is 1. What's right after the 1?
2.
The first number listed here is 1. What's right after that? 1. Row 1. Oh. First number listed here is 1. What's behind that? Nothing really. 0. Okay? What do you think this row would be?
3.
What do you think this row would be?
4.
What do you think this row would be?
5.
Okay, you see the pattern?
No.
Who said no?
Take a guess.
You don't see the pattern?
I see it.
Okay. All right. So what are the values in row 7, kids?
7.
1, 7. Okay. So that second number always tells you what row you're in, right? As you read it left to right, that second number always tells you what row you're in, okay? Well, kids, I'm going to make this very easy for you today. Pascal's triangle helps a ton with binomials, and here's what I want to do. I know I'm going to run out of room. I know I'm going to run out of room on the x minus 3 part here. But the thing about Pascal's triangle is this. You can only use Pascal's triangle if you're treating it as an a plus a b. Okay? So here's the situation, and hear this. In this example right here, a is really what variable? X. But you can only use Pascal's triangle with binomials a plus b right here. So the b value, up top we were just taking the number on the end, whether it said a minus b or a plus b according to a formula. But in this situation right here, if you're going to use Pascal's triangle, and if you treat it as a plus b, what's the b value really going to equal in that first example? -3. Okay, so here's how this works, kids. First thing you're going to do is identify your a value. What is a equal to? And what's b equal to? Okay, now, what power is this to?
4.
The 4th power. Okay, you're the 4th power here. Okay, here's how you expand this using Pascal's triangle. We are going to be row 4 then, because our degree is what? Okay, look at your 4th row, kids. What are the values in the 4th row?
1, 4, 6, 4, 1.
1, 4, 6, 4, 1. Okay, now, I'm going to put my work for this box on a bigger sheet because I know this is going to get kind of lengthy for me. I'm not going to be able to fit that in here. So let me get a clean sheet right here. Here's how this works. Okay, what was the function again? X minus 3, was that right? To the 4th power. And we have to expand that using Pascal's triangle. Here's how this works. First of all, always start with your first one with a power equal to what's out here. In other words, your first term is going to start out as a to the 4th. Okay? Your second term is going to start out low, 0. And what's going to happen is that first term starts out, don't look at this, okay? Look at my hands. If I start out here, high up here, okay? If I'm up here at 4 for the first one and 0 here, then the next time, your first highest exponent for the next term is going to come down 1, and that lowest term, that exponent is going to go up 1. Okay? Does that make sense? Make sure you're looking at my hands. All right? I'm not going to sleep well tonight about this. All right, here's how this works. You ready for this to expand it?
Sure.
Here we go. Remind me again in Pascal's triangle what the 4th row values were.
1, 6, 4.
Okay, here's how this goes. Your first term is based off of the 1. You're going to bring that value 1 down here, okay? You're going to start out with 1, okay? And then you're going to have times your first term in here, which is what? X. And you're going to raise that to the high as you can go. What power are we at? 4. And then your b value is what again? To the 0 power. That's how you start this, okay? Your first term is your highest power. The second term always starts out at 0. Okay, now, to move on to the second one, we're going to use these coefficients in the triangle. What's the next coefficient here? We're going to put a +4. Now listen carefully on this. This is going to become 4, but my x's, what's going to happen to the exponent? It's going to drop down 1, and this one here is going to start moving up 1. Okay? Basically, one exponent starts here, one starts down here, and they just start working their way back. Okay? And I'll show you here in a second why this works, but hang on there with me. We're going to have now 4 for the second term. We've got to bring the x in to the what now? 3rd. And then negative 3 to the what, kids? Negative 3 to the first, okay? So we've used up 4. Anybody want to guess what the next term's going to look like? Plus 6 times x to the second. Bring the x down 1 times. You guys are golden. You've got the pattern. What's next? Plus 4 times x to the plus 4 times x to the 2 is going to turn into a what? And then when negative 3 is out here, power of 2 is moving up to, okay, and then the last one will be plus 1 x to the all the way down to the what? Negative 3 to the, okay, now there's a lot of writing, okay? But you understand the pattern with me first. Okay, every time your exponents right here, 4 and 0, what's that add up to? What's 1 and 3 add up to? 2 and 2, 3 and 1, 4 and 0. Why were we in row 4 to begin with? Okay, and your powers are going to work their way down. How many terms did I have in this row? Or coefficients? How many terms do I end up with here to go? 4, 0, 3, 1, 2, 2, 1, 3, and 0, 4. 5 of them. That's why we're using these, okay? So let's do some simplifying now here, kids. It's not too bad. Hey, it's not too... Look, you want the hard part to this?
No.
Okay?
Yeah.
There's a harder part to this. I can make this really difficult if you want. Okay? I can make you multiply this 4 times in a row and then combine terms. Or we can do it in 2 rows. What do you want to do?
No.
Okay. So what's anything to the 0 power going to be right here, kids? 1 times 1 here. Still 1. So this first term right here is just going to be 1x to the what?
To the 4.
Okay. All right, so let's talk here. Help me out here. How about negative 3 to the first power? Negative 3 times what other value here? Negative 3 times 4 is minus 12, isn't it? So this becomes minus 12x to the... Okay. Third term. Help me out, kids. What's negative 3 squared in this third term? 9 times the 6? 54. 54 what? Positive 54x squared. So I'm going to write plus 54x squared. Okay, next term. We're getting there, kids. What's negative 3 to the third? In other words, negative 3 times negative 3 times negative 3. Negative 27. So I've got this part to be negative 27 times 4. I'll just tell you that's minus 108 if you punch that up. So it'd be minus 108 what? We're getting there. Last one. Oh, hey, what's x to the 0 going to equal? 1 times 1 is still 1. So we really have negative 3 to the 4th. Negative 3 times negative 3 times negative 3 times negative 3. Positive. Think of it this way. 3 and 3. That's 2 of them. 9. 3 and 3. 9 and 9. So plus what here, kids? There it is. Oh, no. That is the shortcut. Who asked for a shortcut? Is there a shortcut? Jasmine, was that you? Jasmine Bush. That is the shortcut. You want me to do it the long way and show you how much longer it would take?
No.
Okay, because I'll tell you this right now. The long way here is probably 4 times longer than that. Let's not do that. I agree. All right? But here's the nice thing about it. Most times they're not going to make you go past the power of 4. Okay? So if they do, I mean, here's the deal. What if I said go to the power of 7? You can still do the 7th power in 2 lines. If you had to do the 7th power, you would have let's see.
What about the 10th power?
10th power, you can still do it in 2 lines.
That'd be crazy.
Okay? 10th power, you can still do it in 2 lines. The deal is this. If I said don't use this rule and do the 10th power, it would take you about 42 lines to do it compared to doing just 2 lines. You don't want to do that, do you? Okay, so let's try one. Let's try one together, kids. What's the other one say?
Oh my god, no.
Okay, we're going to use Pascal's triangle to do what here?
Expand.
Okay, how about this? Let's get this one done and we'll save the rest for Monday. Is that fair?
Yeah.
Okay. And again, well, it won't take long to get that plan on. A lot of time to work on this Monday. All right?
Yeah.
Okay. The nice thing about this, what row are you going to be in?
3.
So are you going to have more terms or less terms in the last one? Okay, so I'm going to take this example. I'm going to write this on a separate sheet. So that next example was 2y. What was in parentheses? Plus 4. All to the what?
3rd.
Okay. So
Have you ever done
what row am I going to use?
Ow.
Row 3. So what are my coefficients going to be?
1, 2, 1. Oh no. 1, 3, 3, 1.
1, 3, 3, 1. Okay. And the way I always think about it is this exponent is the same as the second number in that row. Okay. The second number always kind of tells you what row to be in. Does that make sense? The exponent should match the second number of the row you're in. Okay. So let's do this. 2y is going to start out at a power of what?
3.
And 4 is going to start at a power of 0. You ready to roll?
Yeah.
Help me out. I'm not talking.
Oh,
1.
Okay. Parentheses. Wait, is it 2? Yeah. 2y. Third. Parentheses. 4. 0. Plus. 3. Parentheses. 2. Y. To the second. Parentheses. 4. First. Plus. 3. Oh my gosh. Oh, you're just going. Oh my god. Oh, right.
Oh, did I just hear somebody that's like Harvard in here? I love that. That just made my day. Somebody that's like Harvard in here, and that just totally made my day. No, really, it's not. You're just following a pattern, aren't you?
Definitely not like the one.
You start going around to people's houses and writing this stuff on windows with markers, I will start to worry about you, though, okay?
That's what the real Harvard graduates do.
Okay, let's talk, kids. 4 to the 0 right here. Well, back up. Do you understand how I wrote that first line?
Yes.
It's so fun. Sorry. Do you guys understand how I wrote the first line?
Yes.
Do you understand the pattern for the first line?
Yes.
Okay, do you understand the coefficients we use from Pascal's triangle? Okay, so let's check this out. Guys, 4 to the 0 is what value? 1 times 1 is still 1, so we have to cube 2y. 2 times 2 times 2 is going to make what? So this first part right here is going to become 8y to the 3rd. Yep. Okay, now it gets a little trickier. My suggestion, start with anything that has a variable in it. So don't we have a 2y squared in this second part right here? Okay, what would 2y times 2y be?
Okay.
So the middle part's 4y squared. 4y squared times 3. 12y squared. 12y squared times this 4 to the first, which is 4. 12y squared times 4 would be? So this becomes 48y squared. Okay, next one. 2y. 2y to the first. So is this changing at all? No. So what's the 2y times 4 squared? What is 4 squared? 16 times 2y is 32y times the 3. So plus 96y. And then the last one's not so bad, because 2y to the 0 is simply going to become what? 1. 1 times 1 is still the 1 here. So this is really 4 to the 3rd plus 64. Okay? Guys, Pascal's triangle makes it so that you can expand any binomial to any power and do it in how many lines? 2 lines, okay? Now, can the numbers be a little complicated?
Yeah.
Absolutely, but my question is this. It's okay if the numbers get complicated. Do you understand the process? That's my question. Okay, let's stop there. We'll finish that last example on Monday and have a lot of time to work. You guys